Good evening. We're just starting off to the races again. I'm going to do the lecture in a particular way that I think is going to be a good way to go for us tonight. We are essentially about to start Chapter 4. I'm going to cover a little bit of stuff I didn't cover in 3, very little. It'll be more important for the first project, but that's something I didn't get done last week. But before we get into 4, what I want to do is go over the old exams, give you some comments about that. I made comments informally last week about the crib sheet, but I'll make that formal tonight and go over some specifics that are actually in those old exams too, like problems that, I'm going to be giving you some hints, so just pay attention. Will it definitely come true? I don't know. I've already worked together the exam from old exams that I have. I did that over the weekend. I took a good look at it, and I thought a long time about it. I haven't made it the real deal yet, but it's gonna come pretty soon, and it's going to be on my mind. It's kind of my priority to get that behind me so I can make sure I get it printed and so on. But before we actually do that, this was an exciting thing for the day. This was the day that in the electronics maker community and other things that most of us might be involved with, I think all of you have used an Arduino at least once in your life. Today was a big day that they announced about 2 weeks ago, and they said you got to set your calendar to get up early. For me, we would have had to been up at 6 a.m. to watch the live stream. It was coming from Italy, so for them it was in the afternoon, but for us it was in the morning. A big announcement, something new and big, and I knew it was going to have AI in it for sure, but it's not really as big an AI product. Probably the biggest thing, though, is that Qualcomm is buying Arduino, so that's a really big thing, I think, that they're selling out, but they're going to keep their threads. I don't know much more than this because I only listened to part of the stream. I managed to get hooked into it after a delay, but then I went off to walk my dogs. I came back, and I simply could not tap my space bar and have it start up again. It just wouldn't find the link again. They say they're going to have a permanent link to the intro, but this is the new product. It's got it sells for $44 pre-order. It's going to be available at the end of the month, and it's got a Qualcomm controller on it that is an embedded Linux type controller, and then it's got another big chip over there, which is an ST microelectronics real-time microprocessor of some sort. So, and it says real-time signal processing is one of the things, real-time video and other things. Lake already noticed what that is. That's an array of pixels or LEDs for doing some sort of cool stuff, I guess. An all-new development environment and some other stuff. So if you're interested, and it won't disrupt your studying because I don't want you to goof off too much, but this is me. This is how I made it through all the time, was tinkering with stuff. Just type Uno Q, and then you'll find links to it. It's kind of exciting. The reason why I get excited about it because I think back to all the capstone design projects over the years since the Uno came out, which today's talk said it's been 20 years since they started. It showed up in a lot of different projects in this department, so I know that it's had its day here for sure. And then I was instrumental in getting that change made to do the Arduino robotics kit from SparkFun, which some of you use that, right? That SparkFun kit. I had bought, pardon me?
I have before, yeah. I don't actively use it.
Well, you did have a class that you used it in, though, right?
Yeah, like the very first class ever, pretty much.
Yeah, and that's what it was for. I could ramble on that, but I won't. I mean, I just got engaged in it, and I thought we should do something very different in our department as opposed to what we were doing, and I had to do some talking, but I got everybody on board, and we made the change. So I guess I'm not going to go there. So now I'm going to talk about the exams. And I'll just say what I want to say about the exams that I'm repeating from last week. Well, let me go back to the very beginning. We agreed last week we'd have it on the 14th. Is that still thumbs up, what everybody wants to go with? Okay. I'm fine with it. The way it will work, I don't dedicate the whole week's worth of lecturing to the exam. That's overkill. You don't need that much time, and it'd be just kind of boring. So what I generally will do, we'll lecture for about a half an hour. We'll have a break, like a 15-minute break, and then come back in and start the exam, and then work until the end of the class period, something along those lines. And of course, in that first half hour, I'll probably be talking more about sampling theory, but if there's some last-minute questions, I can handle that then too. So that's kind of the time format. We have the day of the 14th, and then if you want me to, I will make copies of the math cheat sheet, but if you've already got yourself covered because you already printed it just to have to practice with, I won't do that. So does anybody want me to bring in copies of that sheet? You know what I'm talking about, the formulas page.
The formula, or like the transform?
Yeah, and the series sum formulas and Z-transform Fourier, yeah.
Oh, that will save us so much room on the cheat sheet.
No, it doesn't go on your cheat sheet. You're allowed to have that. You're allowed to have those, and if you printed them off right now, you could be studying them, and then I'm going to let you have one two-sided sheet of your own study material. I was just asking, does anybody want me to bring them? I might bring, copy some off, but yeah, and that's what I really want. I want to know, do you have that? Because if I don't bring any, like one or two, then I won't have any to share. But it was your responsibility to say get your hands on it and understand what's on there, because it's kind of complementary to what you're going to put on your own crib sheet. Like, oh, that's over there. I don't need to do that. I need to do something else on my sheet. And if I was you, I would be probably looking at these old exams and reflecting on what the homeworks were, but more on the exam questions, and say, okay, I might need some hints, or I see some of the things that were on these old exams. And that's the stuff that you might put on your crib sheet, right?
Can you highlight on the exam sheet or no?
What do you mean on the exam sheet?
Like the exam formula that you provided that we printed off, can we highlight?
Yeah. I don't mind that. I don't want you to fill up that exam formula sheet with all kinds of additional notes, but if you want to highlight things on it, that's fine. That makes it your own, right? It makes it personal. So, I want you to do things like that. What you don't want to do is be, when you take the final exam, let's say, when I let you have open book, open notes, I don't want you to be so laid back like, oh, I'll just sit and look everything up for every problem I come to. That's just not going to work. I've seen people just go blasting through notes and books, and you don't really have the time to do that, but it's just there as an emergency, as a security blanket kind of thing. But yeah, for this exam, you have the minimal material. You should be flying. You should just be on top of it, and then you have those things to look at. So that's behind us right now, so let's look through these problems. This was done my fall semester 2022, which was my last semester as a regular faculty member. So here I put a problem on that was just looking at the periodicity that we talked about the first regular lecture, I think, that sinusoids are periodic unto themselves if their frequencies are a ratio of integers, or can be written as a ratio of integers. And then if you have two sinusoids and you want the combination of those two sinusoids to be periodic, there has to be a common integer in the numerator there, or denominator, that means that it's periodic. Like if one is period 3 and the other one is period 13, I guess 3 and 13 are prime numbers, aren't they? So what's the period going to have to be? It's going to have to be 3 times 13, right? Or something like that. That was just a more obscure answer, or problem scenario. I wasn't really thinking it would have to be, prime numbers, but that's kind of the way that would work out. And I think in this problem, I just went ahead after it when I was getting ready for the solutions. I just did a simple model in Python and just plotted it to see that it's correct. Second problem in this particular case is just looking at a relationship. This is like one of the problems early in Chapter 2. So we have an operator T operating on X to produce Y, and it's just asking, 2 of the 5 different quantity definitions we were going through. Is it stable? You were not given that it's LTI in this case, so you have to use the foundational definition of bounded input. Does it produce bounded output? And causal, we're not given that it's LTI, so we can't look at whether the impulse response is 0 for n less than 0. We just have to go on, does the present output rely on only present and past values of the input? This type of problem, though, has lots of different variations. There will be at least a half a page, somewhat like this, of something. Which of the 5? I don't know. I don't know what's on the one that I've already picked out. Okay, both of the exams have problems like this. And although I let you use Fourier transforms and some of you jumped to Z transform, can't say I was particularly happy with that, but it was okay. I'm done grading that now. But this is going back to the classical solution technique of if you have a difference equation, can we solve at least for the natural response under non-zero initial conditions? What I asked for in this problem, and there's a similar question on the other exam, can I find the zero input response, which is just how the system responds to the initial states it might have as it runs out over time. So there's no input in this case. So zero input response means, I guess I can write on this. So you have to find the homogeneous equation and then find the roots of the characteristic polynomial, and then you get down here to this, the homogeneous response. And that's like the first part of the problem, is to be able to establish that. And then if you're given some initial conditions, in this case, let's see. In this case, I just asked for a general solution. No, never mind. Here's the initial condition. So now I'm telling you that y minus 1 is 1 and y minus 2 is 3, and then find out what a1 and a2 are just by plugging in to the homogeneous equation, general solution, and then setting that up from the homogeneous equation, where we're going to say y of n is equal to, down here, 5, 6, y of n minus 1, minus 1, 6, y of n minus 2. So find out what y of 0 is. From the difference equation here, it's 1/3. And also from our general solution, we find out that y of 0 is equal to a1 plus a2. Do that for the next value, y1, and plug into the general solution, y at 1. And then we have 2 equations and 2 unknowns, and then you solve, in this case, for a1 and a2. So I'm planning on giving you a problem like this. I'm just going to tell you right now so you can at least practice at it. I don't think it's too bizarre. It's just saying I can work with a difference equation. I can do a little bit of solving. It's not that much radically different than solving partial fraction coefficients, but now you're just solving it with a difference equation in the time domain. So I think, John, you're the only one that solved this problem using the classical solution, but there was a complete solution. It wasn't just the homogeneous part. The rest of you used Fourier techniques or Z, but I'm not even hinting that I might. I'm saying I'm like 99% certain I will, just because I think it's a nice little exercise to do something like this. Okay, so this is something I said that I could do too. Give a sort of a theorem problem. This one is given x of e to the j omega is the discrete time Fourier transform of x of n, where x of n is real and even. You're given that x of n is real and even. Show that this alternate formula can be used to compute the inverse Fourier transform x of n. So in a problem like this, actually, the thing that comes to mind when you have to do anything like this is which direction you want to go. So in this problem, you're asked to show that x of n is equal to something. So that's where you should start. You should start with the definition of the inverse Fourier transform, then expand it in such a way that you can make the simplifications. Does that make sense? And that's the way I did this one. The problem, if I give a problem similar to this, it could be a theorem, in which case then you could either choose to prove it going from one domain to the other domain, and that would be legal. It's like if you're given this is on the left side and this is on the right side, you might start here and show that you get that by direct analysis, or you might start here and go backwards. If I do a problem like that and I don't give you a hint, like I suggest you start here, you're just going to have to pick, but you'll have the option of bailing out, right? If you start and you say, wait a minute, I don't think I want to start it that way. Just make sure that you do things clearly, and I'll probably bring some extra paper in, or you can, the first thing I'll do when I hand out the exams is I will say, remove the staples so that you have pages that you can flip over, and I want the staples out anyway, because when I get done, I'm going to go up to the office, I'm going to scan the documents to convert it to a PDF so I can be grading it on my tablet. So that won't be a problem. So using both sides is perfectly good in this instance. So some sort of analysis like this will probably be happening. Here in my solutions again, I did some stuff. This is the answer to the difference equation problem, though. That's the initial state running off over time, which we looked at last time. Now we have a systems example. This one just asks you to do some sketching. So one of the things I like to do, and is really going to be coming to the forefront in Chapter 4 when we're doing sampling theory and multi-rate sampling, behind this problem, there was a set of axes already drawn. So I give you a spot to draw everything, and I'm pretty much telling you I want you to do everything. And I'll probably do things like that anytime I need that, because I want you to just have sort of a framework to work in, and then I can grade things. So in this case, I'm asking you to produce 3 different outputs on the interval minus to plus pi. So I'm like your elementary school teacher. They gave you a worksheet mostly with the graph paper already there. Is that good? I mean, it helps me grade for sure. So you can just follow this one out unless you have looked at this and have a question for me on it. I think it's pretty straightforward to follow it. And obviously in this problem, something that will be true in problems you've already worked. Here you're being told it's an ideal filter. It's an ideal low-pass filter. So you have that true, and then you can go ahead and do some sketching. And you have frequency translation going on there, and this sinc function is, for a transformer, that is a rectangular response, right? So it just all works from the tables and the theorems, and I have found that when I'd give problems, I would say, just give me, you know, that spectrum. What would happen is I get something that I can't figure out. How did you get that? So in this case, I'm actually wanting you to be methodical and not try to jump to the end, because I don't think you should expect yourself to say, oh, it's obvious, I know the answer. Don't do that to yourself. And I'm not, in this case, I didn't let you do that, because I said, let's take it step by step so I can follow where errors might occur, and then I can give partial credit. I'm not sure if the exam I've been considering, or the problems I've been considering similar to this, would be like that, but don't be afraid to take it step by step, because that helps me and it helps you. It'll help me see what steps you took to get there, and if you screwed up on step one, then it'll help me understand how everything's got some flaw then from thence on. This is just a simple factoring problem. And see, I didn't require you to have to use the quadratic equation or anything. The roots were already figured out there. But in general, and I guess this comes up in the next problems, if you have to find a root, they're going to be real roots unless I say otherwise. I might say no, complex, if that was the case, but I don't think I really plan on that. So just figure out the root, and if you have a tool on your calculator, and you are allowed to have a calculator, by the way, but devices that can do wireless and things like that are not allowed, so you can do that, but the roots should be easy enough to find. So here is just pole and zero plot, and then possible regions of convergence, like what we talked about 2 weeks ago, I think.
Yeah. With the ROC, does it have to start and end at a pole, or start at a pole?
The edges of it are a pole.
Okay.
So like if we can't go out to infinity, we don't have an example of that here. This can go out to infinity for its region of convergence, but if there was some strange configuration that had a pole out at infinity, then we would have to have it be less than infinity, and we know how we can do that actually, right? If we just have the sequence like this one, and we back it up to the left by 1, then we would get something out at infinity, and then that would change this. And we can do that if we multiplied by z to the plus 1, I guess. That's what would do it. It would shift it to the left by 1 sample. I think is all it takes to do that. I'm not thinking about that, though. I'm not thinking about something quite like that. There are some homework problems that I probably didn't assign, but this was more fundamental. I think this is the type of thing that you want to be aware of.
One more question.
Yeah.
So with the ROC, if you have a pole at 0, would it necessarily, and that's the only pole, would it necessarily go out either to infinity or up to infinity?
It would go out to infinity. That's like delta of n minus 1 is that case, right? Didn't you have that in the homework, I think? No, that's the opposite of that. Yeah, there's a pole at 0, and you can't go to 0, but you can go out to infinity, so. Okay, this problem looks kind of busy. It's a cascade, So I gave you the input, and this is very similar to homework problem you had already. It's a problem that forces you to have to work in the Z domain for part of it and then work in the frequency domain for the other part of it. So you're given, kind of like that homework problem, you're given a constant plus cosine. And you want to do the cascade, so you want to find the product H1 of Z and H2 of Z, multiply them together. In this case, there's a pole zero cancellation, so it's a first order system. So that's that part right there. And then find the DC term. Then you want to find what the gain is so that you can find the output, because you know that the output is the input times the system gain and phase shift. So DC, you just need to know the DC gain, and that ends up being 12/7. And then at the frequency 0.4 pi, you just evaluate again. And I used my calculator to just get it in polar form, 0.9330 angle minus 1.53 radians. So then you can come down here to the last line. Pretty straightforward problem, but it's a type of thing that could be very useful in an application, I think, even too. You're putting in a particular frequency, you see a DC bias come out, and then you're wondering what's going on here. Oh, there's whatever that gain of the system was at that frequency, and then the phase shift that gets applied. And this is something we talked through, but I think it might be in the table too. The energy of a sequence is just the sum of the magnitude squared. That's just the discrete time version of energy in a sequence. You don't have, like if you'd integrate the magnitude squared of a continuous time domain signal, then you have a dt in there. But in the discrete time domain, you just don't include dt because you don't have any dt. It's the sequence values are spaced at 1 unit apart, so the scale could be applied later if necessary. So this was really just a let's do geometric series problem is really what it boils down to. I say over here joules, but you can't really say that unless you were saying they were 1 second apart. And then it doesn't even really make total sense unless you needed to approximate something in the continuous time domain. So I think that's one page here. So we're given a causal system, and notice I said real poles, so that was just your hint that when you factor it, you're going to get real roots. Region of convergence, find the difference equation, find the impulse response. This problem, there will be a problem of this variety, but the questions that I ask will probably be different. Maybe I want the step response. Maybe I just want to convolve a particular input with h of z and do that. And maybe I want the frequency response rather than the difference equation. All kinds of, they're all related to that same type of formulation that we went through. It's that last example, I think, in Chapter 2. It's variations on that. And then this is also foundational in the Z-domain stuff where you have to use the partial fraction expansion. So speaking of that, you look at this one, just make sure, and if you want to be pedantic about writing things on your sheet so you don't slip up, you might write a note there and say h of z proper rational, or before you start the part down here where you have to do the Z transform stuff, just notice that, impulse response proper rational, so you can just dive right in and do that. I'm not going to tell you have to use long division. I'm going to let you decide whether you need it or not, and if you don't do it and you need it, your answers are wrong, usually, unless you're a genius somehow or another. I've not really ever seen that happen. There will be questions on poles and zeros, regions of convergence, probably in more than one problem. Look reasonable?
Is this chapter 1 and 2, or is it 3 as well?
It's 2 and 3 is what it really is. It's 2 and 3, yeah. Yeah, 1 was an introduction.
Okay.
So it's 2 and 3. Last year's, which I had my tablet going, so I wrote out my solutions using my Apple iPad. This is just another system. This is one that's in the book, I believe, too. Since you see that one here, don't worry about seeing it again, but it's a mysterious problem, because when you first look at it, you look at that and it looks complicated, but then but this holds true for really any problem you might work. If I give you some relationship like that, think back to the beginning of chapter 2, I just say find the impulse response. Notice how I started it. I put in delta of n, right? Just do it. Don't try to say, I have to do something else. No, just do what you're asked, and then start going from there. So in this particular case, what I think, and this could come up with another type of problem, you look at this and you say, delta of k plus 1. So when the sum index k hits minus 1 is when this delta is active, right? So that's going to say the only term out of this sum is going to be when k is equal to minus 1. And then I can get this simplified. And that's this expression right here. I put k is equal to minus 1, and then got it, and then see that n has to be greater than or equal to minus 1, and then 0 otherwise, and then you can put it all together. So I call this a camouflage problem. It's kind of like something has been camouflaged by just the way it's written out, and but that is very, very true from my experience in working on real problems where you're given somebody's code and you see what their algorithm is, but you don't recognize exactly what type of filtering algorithm it is, and you have to kind of write it out on paper and just kind of puzzle it out and say, oh, that's all this is. And that's kind of what this problem, I think, is in a slightly different context. I mean, the mathematics won't be sitting there usually if you're given somebody else's code, but a non-electrical engineer could write out a filter, though, that would be something that we're not familiar with, and you'd have to maybe think about it more. Causality question, I mean, this one, because it's LTI, you can answer that immediately. And the stability question, since it's LTI, you can go from your impulse response and go use the theorem. I really like this problem. It's not available to me because I had to give you 2024, so I'll have to come up with some other problem. Some similar ideas, though. I know what'll happen when you see the exam and when you get it back graded. You'll say, I wish you would have had one like on that exam or that exam, but that's the way it'll be, right? You just won't, you've already seen it, so you got to have something different. I know when I studied old exams when I was a student, you always thought, if I would have only had a problem like that old exam, that would have been better. But have you had any experiences where you said, I'm glad I didn't have one of those? I mean, you looked at an old exam and you saw a nasty problem, and your exam didn't have one like that, and you can be thankful you didn't have one of those. Have any of you experienced that?
Yeah.
Okay, cool. Ensemble averaging or something is what I call it. You know, what are you going to get? Okay, this is like the other problem where we have the characteristic polynomial and we're going to solve the homogeneous equation. So this problem is just another variation on what I've said I'm planning on giving. So you can study this one. could have been a homework problem, but instead it's an exam problem. It's looking at when you convolve an a to the n u of n with itself, what do you get? This just forces you to write out the convolution sum expression, and that's what I did. I wrote down I have to do a convolution. I have to take one of these two left or right side and replace it by k, and the other side has to be replaced by n minus k. Just jam them together, and then you don't want to sum from minus to plus infinity. Nobody wants to do that on an exam. It's like, I don't think I can do that, right? I mean, one of the homework problems, he had to split it in half, sum from minus infinity to minus 1 and maybe 0 to infinity. But the big important thing is here is the unit step function gates everything. So you look at the unit step and just say it's going to turn on for k greater than or equal to 0. So that is one condition. And then the other condition is this turns off when k is greater than n. So then that takes your limits down to this familiar case, 0 to n, and then you can go in and do it. So think smart when you're writing out sums. If you have unit steps or deltas and things that appear in the argument of the sum, just kind of lay into that immediately, because that'll help simplify matters. Don't carry it down to another line where you haven't gotten rid of something that's really challenging to deal with. Okay, this was the theorem type question on this one. Just prove this one, and I think this one is done in the notes. Just show that nx of n Fourier transform is j dx of e to the j omega over d omega. If it wasn't, it's just a new theorem. So I started in the frequency domain in this case, and then I wanted to get back. So I'll let you think about it. I guess if you want to try doing it in the other direction, that's fine too. I haven't really studied this one. I just know that you just have to set it up carefully. And in this particular case, we're not going to quibble over whether or not we can bring the derivative inside here. I didn't even show a line of that. I showed that there's a derivative over here, but I just right away moved it inside the sum and then let it operate and do its thing with respect to omega, and then start factoring and getting it to look like a Fourier transform again. So when you get done, you have that left over, and that must be what you're Fourier transforming. Okay, oops. So now we're finding the frequency response, very much like one of the first two homework problems on set number 2. Then we want to get the steady state response to an input 5 cosine pi n, and that we discussed that in class one night. We know that for a real sinusoid, the response to the real sinusoid is just going to involve the magnitude at that frequency. In this case, it's pi, and then the angle is going to go inside the argument of the cosine. So we get a gain of (48 over 10), and then we multiply that by 5. So we have, oops, that turned off. That gets multiplied by 5, and then in this case, that angle is 0, because that's the way the problem worked out. When omega equals pi, everything simplified down really nice and neat. I think I probably chose this on purpose to avoid having j's floating around in the math. Will I do that again? I don't know. However it works out. Okay, this one is now in the Z domain. You're given this, the causal signal. So causal right away tells you that the ROC is going to be the largest pole radius, and then you just have to do your factoring. The roots here are real, and it's proper rational, so you can go blasting away to get the inverse Z transform to get you the impulse, or get the signal, get you the signal back. Now in the next problem we have a causal system. Again, it's proper rational, so you can do whatever you need to do, probably down here. I don't remember what it was. I asked for something like it did in the other exam. Region of convergence and the pole and zero plot for the system. And then this one was just finding the difference equation. So what had to be done here work-wise, you've got to just multiply out the denominator, right? The numerator is already the right form. The denominator, though, you had to multiply it out, so you had to get the coefficients from the multiplication. Another Z transform problem, proper rational again, causal. It's kind of boring. Should I try something different?
No.
You answered the way I thought somebody would answer. At any rate, here it is. Find the region of convergence in the impulse response, so you have to just write it out without the pole zero plot in this case. Get the coefficients from the partial fraction expansion and write that out by inverse transforming term by term. And then the last part is now you're going to derive it with a 3/4 n u of n, and this was picked on purpose because of the fact that there's a going to be a pole zero cancellation. So there's a zero in the system at 3/4, and that cancels with that input. So, and what does that do, by the way? This makes you think back to that one question where we had, it was the bonus problem that had the black boxes and had inputs and outputs. This is a situation where the system contains a zero, so the input tries to get in with that mode 3/4 to the nu of n, and the system has a zero sitting right at that same mode, so it blocks it from getting through to the output. And we're ending up with just modes that correspond to the system response itself, the 1, -1/6, and the 1/2, both to the n. So in some cases for me, when I'm looking at problems I'm creating, I don't try to make them so realistic that they just have all kinds of extra fuzzy things around the edges that just tend to get you bogged down. I try to keep it simpler. So this one was probably figured out on purpose to make something simplify. So be on guard for that, because if you're like some people, and maybe somebody did that, if you didn't see that cancellation, now you're just starting to breathe heavier because you've got A1, A2, and A3, and you're just saying, I got to work extra hard to get all these figured out, and then you didn't notice that. I mean, what would happen if you would have not noticed that? Let's just think about that for a second. Suppose you didn't notice there was that cancellation, and you just said, okay, I have 3 poles, and then I have that numerator, it's still proper rational. You would just start solving for these coefficients, and what's going to happen if you had like an A3 to go for the 1 minus 3/4 e to the -1, what will happen in the partial fraction expansion? A3 will be 0, right? It should happen, so it should take care of itself. Good? If you have any other thoughts, you can fire back at me later on Slack. The new homework assignment is out there too, but right now I've picked Friday the 24th as the due date. I don't know how that's going to work out. If I can't make that happen, I will slide it to Tuesday the 28th, but right now I've got it set for the 24th. There will be 2 assignments that have problems from Chapter 4, because Chapter 4 has got a lot of material in it, so. So now I'm going to move over to this is where we left off, and this I think I showed you in both Python. If I didn't show it in Python, I know I showed it in WX Maxima, but that's where we left off. We're done with the chapter, but there's another thing that I put in the Python notebook, the Jupyter notebook for chapter 3, and this is something we're going to see when you work project number 1, and you can be doing some real-time processing. So, and this is what Python offers up with its L filter. So this topic area is called Using the Initial Conditions to Provide Continuity Between Data Frames. So what we saw so far with initial conditions was if there's some initial states like y of -1, y of -2, or x of 1 or -1 or something like that, that we would start our system off with those states non-zero, and then we'd have something already, inside the system that has to drain out. But a more common application of non-zero initial conditions is if we're doing frames-based processing. And we talked about this a couple of weeks ago when I was showing off how you'll be doing real-time DSP. So frame-based DSP means that the A to D converters put together a package of samples, like 1024 samples, 512 or something will come from the system audio, and they will be handed over to the Pi audio helper, and it will be expected to take that big chunk of samples, do some algorithm on them, and then ship them out through the D to A after the Pi audio interface takes it over as a frame and then unpacks it to send out one sample at a time to the D to A. So if we're going to be doing a filtering application in the blue box there, we will have to set up some a state vector that will hold the initial condition, so that if we're doing a filtering operation, at the time when you get another frame, we'll start that filter off not with zero initial conditions. We'll carry it forward from the states that were saved the previous go. Does that sound sensible? I mean, John, you're doing that in the lab, right? So I have some C code in there. We have some filters that have a state variable or an array of samples that are held and passed to the next sample. I mean, the next single sample, but it has an array that's held. So how does Python do that? Python's L filter has a function called lfiltIC. So lfiltIC, if I go Shift Tab on that in the notebook, it says construct initial conditions for L filter given an input and output vectors. So what I don't particularly like about this, and you're going to write a different variation on this when you do problem 1 of the project, you put in an initial state, but what is it is not totally clear. Generally, you're just putting in an initial state for y, and then that makes sense. But how do you put in x? Generally, x, you can see it says x equals none. So by default, it doesn't expect pass values for x, but it will allow you to set initial values for y, like pass values of the output can be stored in y. So what this function does is it returns an array zi, which is dependent upon how the algorithm is implemented, and we won't talk about topologies of filters and things until chapter 6. But zi is a state vector. We can look at it, though, certainly, and I am going to do that here once I run it so you can see what it's doing. Here I just set up an example, though, where I'm going to take a 5-sample moving average filter. So I put in coefficients, 5 ones divided by 5. So just we're going to average over the past 4 values of the input and the present value of the input. The A coefficient is 1, and then I started off with zeros for the initial condition for this kickoff. So I have a kickoff where I generate Zi, a state vector. So now I come down here, I'm defining a cosine sequence. I'm going to define an array that's going to hold the 100 values of the output, because that's what I'm saying. I'm going to simulate 100 samples. And I'm going to initially only sample 0 through 49. Remember, Python, when you use a colon operator, it stops 1 sample less than the top edge. So 0 to 49, which is 50 samples. And I'm going to use B and A defined up above. And I'm going to pass in this Zi that I created right here. So let's just run this. Let's just see what Zi has in it right now. It has zeros in it, but those are the 4 pass values of the input. But I said they were to be 0, so it just set them to be 0. Don't know if that really makes sense or not, but we're just trusting that it knows what it's doing. When I say it, I mean L-filter knows what it's doing when we pass this optional argument, which we've never really used before. But if I go Shift-Tab on this, optional initial conditions for the filter delays. It is a vector or array of vectors, blah, 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 other conditions, and it says CL filter IC for initial conditions. So we're using it, and we have to take it out then. If we put it in, we should take it out again. So it's the second argument that comes out of the function or is returned by the function. And then what happens is this Zi comes out here. And in the case of the Pi Audio helper, the next time it calls the callback, it will pass this Zi value back in again. Here I'm just doing it one after the other. You could say, that's silly, why don't you just filter all 100? I'm just trying to show you what it would be like if we had to do 50, and then a while later we do 50 more, and it would be a continuum of samples. So, and I'm doing it in a very nice way for plotting. I use a left side argument that says pass the outputs of signal L filter into 0 up to 49. That's one of the cool things Python can do. This is kind of a special deal, right? You can say, I'm giving it X, but I'm saying only fill at those indices. That's kind of a nice feature that it can do that. If you're writing it in C, you might actually just have to have a for loop. There might be things in C with C++ at least where you could have that allocated. I don't have an example at the top of my head, but I'm sure I may have done that or contemplated doing it. At any rate, pass over the initial conditions from the first pass into the initial conditions now for the second pass. And then I have the output from the second pass will return its initial conditions from the second pass. I'm not going to be using them, but I'm collecting them anyway. And then I'm filling up the last 50 samples. So there it is. I don't have the first Zi, but if I go look at Zi right now, though, it's definitely got some numbers in it. They're different, right? Question?
What are the different numbers in the Zi array? What do those mean?
Those are values that were held in, signal values that were held as a result of the calculations with the difference equation. Like it calculated, the moving average filter says Y out is equal to the pass value of the output times 1/5, 2 pass values of the output times 1/5. So they have to do with values that were contained in X. because those were values that were used in calculating this difference equation. Actually, because this is done recursively, I'm not sure where they come from. That's one of the things that's confusing. All I know is that they're related to the input signal. They're not related to the coefficients. They're related to the signal itself. So here you can see the moving average filter is ratcheting up because it's averaging with 1 sample, 2, 3, 4, and then finally 5. So what's that called in circuit theory? Starts with a T. Oh, in circuit theory, what do you have at the beginning of the output where you've got something happening? What do you call that? Transient, right? So it's the filter's going through its transient. It's getting charged up and taking on values. So no discontinuity, though. So now here, I'm being ignorant of the fact that I need initial conditions. I do the exact same thing, but I don't load the initial conditions in and then pass them from the output of the first pass into the second pass. So I do that, and I get this. It's charging up, and then it runs the first array out perfectly, and then when it starts the next subarray, it's starting with 0 initial conditions. And if I was writing real-time audio, or if you're writing real-time audio in your project, you'll hear this glitchy thing going through. It'll be like, what's going on? I hear this kind of glitching thing happening. Or it might be buzzing if it's happening really fast. It'll be something that'll be like, that's an artifact. Where did that come from? And, you know, it'll be something that you'll want to troubleshoot then to fix. So this is actually very nice. I don't know opinions on it. It's life. I mean, in the sense that you can't process all the samples you want to process, so you process a block and then process another block. The simplest and smallest would be 1 sample at a time, but still, even with just 1 sample going through, you still have a state that you have to carry forward. And L-filter lets you do that too. You could just use different frame sizes if you wanted to. I mean, I could have made this 75 and 25, right? It just simply moved it over. It still had to happen, whereas if I would have done this, don't even know it's there. Now, why would I do 25 and 75? I don't know. It doesn't make any sense to me. It would be like we're going to use frames of a certain length, and it might be established by an interface. When I worked at Augustus Aerospace, they had the software-defined radio that brought in packets, and they had a certain frame size established for streaming the data through the receiver signal processing, and it was a variable that I had to expose, and then they would set it based on the frame size, and then it would manage it all the way through. Frequently a power of 2, right? Because a buffer might be some power of 2 samples long. Good? I had to throw this in somewhere, but now you've seen it, so when you see you have to do it in Project 1, you'll say, okay, I remember we had to do this. Okay, like I said, there's a lot that goes on in this chapter. All the way down to polyphase implementation of interpolation filters. Then I break out of the flow and I go and do some studying of discrete time random signals with review of probability and random variables, and then introducing random processes, and then start doing things with random processes down to here. And it turns out that random processes have been included in Chapter 2 and Chapter 3, at the end of the chapter, they just never have been, we've never touched anything with them because I didn't want to be trying to do that at the very beginning. It's a new topic, and it's kind of tough. It's got a lot of definitions and stuff, so I was saving it up for a time like this, you might say. And then we can go off and do some things where it's useful, like oversampling and noise shaping in A to Ds and D to As. The homework problem that you just turned in, it had those feedback connections in it, right? That's a model for a sigma delta A to D converter, which is pretty, I guess I'd say, ubiquitous. It's everywhere. I mean, it's in everything that we do. We have an oversampling converter. Oversampling A to D with noise shaping. And what's so cool about it is we'll go through it and see how the modeling works, but fundamentally what made it such a great innovation within not that many years, maybe about like 20 years or so. It's been around, it's a long time, but still only 20 years. 1 bit. So the converter is only 1 bit. It doesn't have to sample with 16 bits. It can sample with 1 bit of A to D and 1 bit of D to A, but it's oversampling. So it'll be sampling at 64 times oversample, and then it can manage that, and we'll talk about how that works. It's been a game changer, though, in technology in terms of how analog circuit design works. As long as they can clock their analog circuits faster, we can accept the fact that they don't have to use lots of bits of resolution, and that's a good trade-off. It kind of does something that I'll be talking a lot about in this chapter, and that is the DSP people saying, we want to pull that into our domain because we want to have control over it. We're saying, the analog designers, we're taking this away from you, sorry, but we can do it better if you let us, if you could run at a higher clocking rate. Does that sound reasonable? I mean, if you're a megamaniac, you want to do everything your own way and you don't want anybody else to have a say in the matter. So you might say DSP people have been kind of like that. They want to do it their way. But I think that's true of technology in general, why we do different things. Like, I'm thinking of something that hasn't been used that much, but since I know some of you are taking antennas this semester, 5G has the capability to use spatial signal processing so that you can have a spot beam or a beam on your locale, and somebody else can get a different spot beam because of the capabilities of the tower. The tower can use different phasing coefficients. This is a DSP kind of topic. The elements are the antenna design, but how you drive the elements is you can drive the elements with different phase shifters, which is a microwave component onto itself, but you can also control that and make that be the responsibility of the D to A to drive the elements with different phase shifting. At any rate, that's something that is saying we don't want that on the handset because the handset is small. We can't really have a lot of elements on our handset and hold on to our phone and not have this, bigger array. We could maybe use some newer technologies in antenna design with substrates with high permittivity to shrink things down more, but still right now I think the idea is keep it simple on the handset, but put the sophisticated stuff up on the tower. And the towers that are up behind the building have some of that capability already for the multi-element arrays. Anybody thought about that? I mean, it's used in satellite and space and electronic warfare and everything else, array processing. But DSP is kind of wrapped up inside of that in certain ways too. So first thing, and then we're going to take a break. This is just a picture that I created a long time ago, but it takes me through the basics of what this chapter is all about and what DSP in a lot of ways is all about. It's just whether or not you have both an input and an output, or whether you just have the input or you just have the output. So here I'm going to take it all the way through, but a lot of applications it's split down the middle, like in a receiver. Will be the front side. In a transmitter, it will be the back side. And an end-to-end system will have both. And I'm speaking of audio and RF at the moment, but the back side is what compact disc did way back in the beginning in 1976. Seems like a long time ago. Started with the disc having encrypted into the pits on the disc the audio material, and then it could play that back into your headphones. And now we have streaming audio, which is pervasive, right? Does anybody even own a CD player anymore? I mean, I still have one, and my wife and I have a lot of CDs, but I'm okay with iTunes and things like that, just having it that way, because it's much more convenient for me to have. The front end side, though, is kind of, the front end to the back is what we do with the Pi Audio Helper. You can process it all the way through, but we'll be looping back to make it such that you don't have to have a microphone or an input. At any rate, this just shows a signal that's a square wave, which is really not possible because a square wave has an infinite number of harmonics and really can't be captured with a finite sampling frequency. But we will round off the edges of it to band limit it, and we'll get some ringing into it as a result of having an anti-aliasing filter to try to keep the harmonics suppressed so we don't have an aliasing problem there. And then the sample and hold, which is connected in with the A to D converter typically, is going to have a finite bit precision. So you'll see stair steps in there saying that we're approximating it with a finite resolution. For a 10-bit, 12, 16, whatever bit converter, you can't see these in a picture like this, so I exaggerated it just so you get the idea that it has finite precision. We will be able to study that, though, and we will with quantization noise, and that's one of the reasons why we're studying random processes, so we can see the impact of quantization. The A to D uses maybe 2's complement signed arithmetic, so many words wide, so those are bit sequences that are maybe 16 bits wide or something like that, or 32-bit signed integers, or maybe if it's really luxury, it's going to be converted to floats, which is what we do in the Pi Audio Helper and what you do in the board you're using in the class. We convert it to floats, which is like a float 32-bit float from a 16-bit signed integer. And Pi Audio Helper works with 16-bit signed integers, but then we convert it to floats and then let Python's L filter and everything just do it in floats. Very laid back and lazy, nothing hard that way. It's pretty nice. And then we come back out and eventually go from some sort of precision, some sort of format back out to fixed point, probably in a D to A, 2's complement, most likely, D to A. And it comes out with finite precision. So in this case, I'm showing the filter maybe removing harmonics. So it's a sinusoid, but it's still fixed number of quantization levels. And then the reconstruction filter is analog. There might be a sigma delta with a high-order digital filter, making it look very smooth and continuous at an oversampled rate. And we'll get to talk about that too. So this is the end-to-end, and the book calls it, and this is probably about where we'll be stopping tonight, it calls it let's see, it's D to C, no, C to D, continuous to discrete, followed by an H of Z, followed by a discrete to continuous. So it's a 3-box system abstracted into the way the notes talk about it, and I'll just dial up there really fast because the whole is in here. So this is what we'll be studying. The C to D is our high-level model of a continuous to discrete converter with sample spacing cap T, and our D to C is which is like an A to D converter, and our D to C is discrete to continuous with sample spacing cap T, and it's the D to A converter, and then stuck in the middle of that is the discrete time system, like H of Z, or H of E to the J omega, or a difference equation. Fundamentally, the algorithm is a difference equation in most cases, but it doesn't have to be strictly a difference equation, but it's something that works in the time domain. But it doesn't have to be that either, because we can work in the frequency domain. And if I carry through with my plan to have the filter banks and the radio stuff for the final project, you'll get to see how you can do transform domain filtering with the FFT. It's very cool to be able to do things like that, but it's still, in the end, samples coming in and coming out. The transform is just in the middle of it. I mean, the idea being in the discrete Fourier transform, not discrete time, but DFT. So let's take our break, though, and go on this stuff. With periodic sampling, unless you want to cram it through. I ate my Cliff Bar already, so I'm doing okay. I think we should have a break, though. Brain rest for a moment or two. How about coming back at 10 after?
Would you please look at Ubuntu?
Okay, we're back to recording, and we're going to start with sampling theory. And this is a review, but we're going to get a lot more details involved. 2610 is the first time you see sampling theory, and then I don't know whether you see it, to what degree you see it in 3205. There's some cool stuff that we're going to be doing here very quickly. So the notation that the book likes to use for continuous time signal is to have, this thing will work for me tonight, the C meaning continuous. So X sub C with parentheses means it's continuous time, and then if you're sampling a continuous time signal, you put in a discrete time index of n times a sample spacing, and then that becomes the discrete time signal. And T is the sampling period. Most of the time, I prefer to use sampling rate, which is 1 over the sampling period, and that's the sampling frequency, or samples per second. In the book's notation, then, they come up with this idea of the continuous to discrete converter, and it's more of a mathematical convenience thing. We'll talk in this chapter about A to D converters in more detailed models, and then D to A converters, but this is convenient right now for us. It's mathematically convenient. It looks electronically awkward because it's an A to D converter is what we're talking about, and if we want to be very formal about our A to D converter, we can make it abstract and unbuildable, and that's kind of where it's going to be at for right now. It's just a concept. So we have an analog signal X sub C, we have an ideal sampling waveform S of T, and you can think of the S of T as being a switch that opens and closes momentarily, and the momentariness of the switch is so fast that it's a delta. So it's just like ting, 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 getting a sample coming in, and then that gets converted from an impulse train into a discrete time sequence, and that gets talked a little bit more on the next page of the notes, but that is again a mathematical concept. It has to get taken in and converted to a digital word, and you normally would think of that, and that gets discussed more in this chapter, but right now it's keeping it simple and high-level mathematics as being some sort of converter. Like in electronics, you may have learned about things like successive approximation register, and you take an analog value, sample it, and then you go through a register that's a digital register that essentially uses a D to A to count, to increase the analog value until it trips a comparator and it says this is the analog value that we need to have, like 100111 or something like that. That would be a successive approximation register, and that's the older type of converter known as a SAR for successful approximation, a SAR converter. The sigma deltas have pretty much taken this over for analog audio, but then the other type of converter that's used in really high-speed software-defined radios and other applications would be the flash converter, which has a comparator for every amplitude level. So it's a huge array of comparators to instantaneously convert to a digital word. Right now, because mathematics is just trying to abstract it, it's converted to a value. So we just treat it as the sampling waveform, and it's going to get multiplied times the analog signal. And then it looks like in the sample signal domain, we have an impulse train, and the amplitudes or the areas of the impulses are the sample values. So x sub c of nt is mathematically convenient to represent that. And what the difference is, the analog sampled waveform looks like an impulse train at some sample spacing that are multiples of the sample spacing t. And in the discrete time domain, they're just integer values, and they're the areas of the impulses. It's just making it more formal, but what we want to do is get down to the abstraction that we now have a sequence, and we get it from the analog waveform by ideally sampling it. So now we can switch to the frequency domain and carry on to get that perspective, which gives us all the neat things for sampling theory. And I'm going to, even though I'm starting to feel a little bit fatigued, I am going to show you some neat demos that I have, some demo apps that I have of sampling theory in the time and the frequency domain. Not written in Python, though. They were written in object-oriented basic language. Today it's called Zojo, and I'll explain that when we get there. So we need to get to the frequency domain from this product, and we're going to get that by Fourier transforming. And in order to do that, the way I wrote my notes many years ago was I have on the page that follows in the notes the review of the continuous time Fourier transform using the notation that the book likes to use. And the book wants to use capital omega for the analog frequency axis. And then we'll eventually get the relationship over to get the relationship between big omega and little omega with capital T thrown in there. So the inverse, or the Fourier transform, is e to the minus j capital omega t. So this is what I call omega domain transforms. And if you took comp theory 1, that course uses frequency in hertz transforms. But we can work back and forth between them. I'm not going to fight it because it works well in this class to use the omega domain for the Fourier transforms. So the inverse transform gets the 1 over 2 pi, whereas the F domain doesn't. If you're wondering about x of f, you may have seen this before. That's the frequency domain, and then the inverse is just I don't know what you've seen before. In COM theory, we use that exclusively. I don't know what you saw, like in 3205. Which one did you use, omega domain or F?
Well, we use
You use F? Little f? Okay. We'll make it work here because we can make the conversions if need be, but I'm not going to ask you to have Fourier transform tables. They're right here. The ones that we need are right here. So we'll also define a rectangular window function. This is the same as it is in the comp theory class. Capital pi of t over tau. That's just a pulse. And then the Fourier transform of that turns out to be the sinc function. So, well, not directly, it turns out down here, it's related through there's a tau that goes out in front of that. This is, and then the sinc function that has big omega times tau over 2 pi. This is just kind of goofy, because if we were to make the changes in here, this would be tau. How do I get that? It's because omega over 2 pi would be equal to f. We're not doing that in this class, but in case you've seen this before, I'm just carrying that out to show that it's very, very similar, but it's just got the 2 pi thrown around in here. So sinc function is the same as we saw back in chapter 2 when I was talking about it. This is with continuous variables, though. And so these are the main theorems that we need and need to think about a little bit every now and then. The delay theorem, the frequency translation theorem, the modulation theorem, where we multiply by a real cosine, convolution theorem, multiplication theorem, Fourier transform in the limit, where we can transform a delta in time to be a constant, and then the inverse of that. We get a delta function in the frequency domain for a constant, but we have to throw the 2 pi in front of it on the frequency domain side. E minus at u of t, like our RC low-pass filter and other things in the S domain, and then the Fourier domain are there. The rectangle goes to a sinc in the frequency, and a sinc in time goes to a rectangle in frequency. That would be our ideal low-pass filter in the analog domain. And then the last one, and this one actually ends up being one of the most important ones to use right away, is that a impulse train in the time domain becomes an impulse train in the frequency domain with a scale factor thrown on in front of it, capital omega naught. And that's kind of magical looking, but it's consistent with what we saw even in chapter 2 when I said look at a pulse train in the discrete time domain ends up being a sequence of delta functions in the frequency domain. Remember I showed you that? That was just to say that there's at least a consistency. So now we can go back up to here and just say, okay, how are we going to get the Fourier transform of the sampled signal? We can get that through a convolution of the two functions, xc of j omega and s of j omega, and then we have to throw the 1 over 2 pi in there because that's part of the convolution theorem or multiplication theorem in the capital omega domain Fourier transforms. And then we can pull out what this guy is. Oops. That all comes about through that last transform pair. S of t is an impulse train in the time domain, and then in the frequency domain it becomes an impulse train in the frequency domain, and big omega naught is 2 pi over t. That's what we were just looking at over here. But something very nice is going to happen. That 2 pi is going to cancel. So what we always are going to be remembering is when we go to the frequency domain for a sampled analog waveform, we have a 1 over t that goes out in front of it. And then we just take the Fourier transform of the input signal and replicate it up and down the frequency axis at multiples of the sampling frequency. So this could be in hertz or it could be in radians per second. It doesn't, at this point, it doesn't really matter to us. I like thinking of it in hertz, but the mathematics here is in radians per second. It's just going to replicate the spectrum. When I taught 2610 a very, very long time ago, the last time I taught it at least, we never really did this. We just stayed abstracted from the Fourier transform because it gets too confusing too quickly. When you take 2610, you haven't even finished calculus yet, as I'm thinking back. Isn't that true? You still had one semester, or you were taking one semester when you took the class?
I was in DCQ.
Okay. That would be more typical, but it wasn't required for that class.
Yeah.
So now we're going to do kind of a classical frequency domain view, and I'm going to show you this demo here tonight too. I like them both. I mean, I think when you work with sampling theory, you have to be in the frequency domain, but you have to also understand that the time domain is where things are happening most often. So you need to have this view, and the view of the frequency domain makes it so easy to understand if aliasing is present, and also to understand when you go through systems, and that's what the homework problems will be doing. How do you figure out what's going on? You can figure out better what's going on usually in the frequency domain, and that's what this chapter focuses on an awful lot. So it's common to pick a triangle for the spectrum of the input because it's just a nice picture to draw. When I start unwinding after I get back and get the video going on this computer, I might think about a way that you can use the computer to do some of the homework problems. But right now, a lot of the homework problems are going to involve you sketching the frequency spectra. And it's going to be foreign for some of you to not be able to do it on the computer. You're going to have to sketch it, and then you're going to have to scan it and put it in, or do it on your tablet. I know I've done this, I thought about this in the past, but as I was studying this late last night and then going to bed, I was thinking, can I make a contribution in this area by creating some little widgets in Python that can draw pictures for you? I don't know. Do I need to do that? Not really, but it might be nice. I don't know. Some things are just not easy to do on the computer. We still use paper, and I still like having a pad of paper handy whenever I'm working at the computer. Don't feel guilty about doing that either. I think it's totally legit. I think some things are still easier to sketch out on paper, and if we ever get away from that entirely, I think we've given our lives over to AI or something. We're not able to use our own brains to think through this. We might have some tools, but I may give it a thought, or I may read about the new Arduino Uno Q instead, because that sounds a little bit more exciting to me, personally. Okay, so we have a triangular shape, and now we're going to consider, we're going to sample that at some sampling rate, and the sampling rate is going to be omega sub s, and we're going to choose, in this particular case, omega sub s to be greater than 2 times omega sub n. So that guarantees that these triangles are all distinct, they don't overlap one another, and this is called being alias-free. There's no spectral components that overlap to produce aliasing. If over here, though, we let the highest frequency omega n, and that's what capital omega n is, if you let omega s be less than 2 times omega n, then we're going to get some overlapping, and we'll see aliasing taking place. We'll have the spectrum starts to get cluttered up with components that translate down into the band of frequencies of interest. And this halfway point we'll be talking about is generally referred to as the folding frequency, or the half of the sampling rate, omega s over 2. And when the signals come close together and they actually cross over, then we have aliasing. If we are alias-free, then we can get back x sub c of s from the sampled signal by just using a low-pass filter. And the simple explanation of that is right here. We're going to bring in our sampled signal with this apparatus, the sampler, And now we have all the spectral translates present there at the input, but then we put a low-pass filter in, and we can pull out, or pluck out as well, I like to think of it, the component at 0 hertz. And the picture of that is just like this. You start at the top of your analog signal, then you're going to draw a picture, and usually when you draw this out for your homework papers, you're going to draw this stacked up. So you'll have the first line might be the analog signal, then you'll sample it, you'll sketch it out like this. You might put in some other notation in here, but for starters, it'll be like this, and then we'll switch to the discrete time domain when we get further tonight before we leave. So we have the sampled signal, and then if we have the analog recovery filter, ideal low-pass filter with cutoff at omega C, as long as it can sit somewhere in here, it won't disturb taking out part of this desired signal, and it won't let any of that spectral translator alias leak in, and then we can get what's over there at the end. We get it back again. Now you're probably thinking, that's well and fine. Is that all there is to it? In picture form here, that's all there is to it, but there's more to it, mechanically speaking, than that. And the reality is there's no signal that would be band limited like that. There's no such thing as that. This is one of the puzzling things about the frequency domain and the time domain. A signal that's time limited, like just a rectangular pulse, it has a sync function, so the spectrum goes out to infinity, right? And if you think of the dual of that, just flipping your transform pairs around, a signal that has a sync function time domain response has a finite spectrum. Those are the two extremes. Can we deal with signals in reality that run from minus to plus infinity? Not really. We can approximate that, though. So what we end up doing is just saying we're going to make sure the alias components that might be present in this triangle here or up there are way, way down here, suppressed, 20, 30, 40, 50 dB down, so that the components that would feed over from this guy and leak into this band pass or pass band area around 0 hertz are many, many dB down. Our human hearing wouldn't see it. The spectrum analyzer would barely be able to show it if we were doing a spectrum analyzer plot. We'll be able to see that in our analysis modeling in Python, and it works out really well because we are working with double precision floats, so we'll be able to see things, and if we can just decide upon what makes it safe and acceptable, we can use it, and we don't have to worry about having artificial signals. But artificial signals like this are nice just to get started. Would you start a design by just having some very realistic signal that's hard to manipulate on paper to see if your concept even has a hope of working? I don't think so. I think that's just expecting too much. You would start with something simple and prove that the concept has value, and then you would go from there. Does that seem reasonable? So as I said, not recoverable if we do have aliasing, and so we'll get into the sampling theorem here in a second. But now we're just going to take artificially, again, we're going to assume that we have an infinite time waveform, like a cosine wave, cosine omega naught t. I mean, whenever we write this down, we're sort of making the assumption when we do that it runs for forever, but it really just runs over a long enough time that we know the spectral lines are approximately the delta functions. And we actually played with that, remember, where we windowed a sinusoidal sequence and looked at the spectrum and had those spectral blobs, but if we took in more and more samples, it was more compact and it was more realistic, or it was more useful, like in a practical setting. But this is, again, just convenient for drawing pictures, and you've got some homework problems where you're going to be working with triangles, working with sinusoid delta functions, and trying to think, since I was practicing with one of these problems last night. I'm not going to guess at it because I don't remember if I got it right or not. My tablet is sitting at home. I drew it out on paper and I worked the problem just to see how hard it would be for you guys to work, and I decided to put this problem in the assignment and take something else out that I had used in the past that was more abstract. So you got a different problem than what I've used last year. I like the way it worked out, though, and I've already got the hints written for it, so I think we'll find out how well you like it when you actually have to work it. And I know you're not going to start it now. You're going to do two things over the next week. You're probably going to make sure you're okay on the exam, and then you might take some time to get going on this. Meanwhile, myself, I'm thinking about the project and refining some of the problems on that, and you're going to be getting engaged on that stuff too. Like I said, you're going to be multitasking for this class. After this exam is over with, your life's going to be more complicated. Sorry to say, you're going to have to do more than one thing at a time. Can you guys do that?
I can do it.
Yeah, I know you can do it. You don't like it though, right?
Huh?
You don't like it as much, probably. I mean, I grumble a lot at home, and my wife gets kind of impatient with me, but I always say, can't it be easier? I mean, sometimes you just wish things could be easier. Like, I only had to do one thing at a time instead of 5 things, and then, with my hand messed up here, I had an incident, 2 incidents last week after grocery shopping, but I was trying to pull out, I like to eat berries a lot, so I was trying to get one type of berry out without doing one thing at a time like this, and I realized I got myself in kind of double jeopardy with this hand, and I just couldn't do it because I was going to cause a lot of pain. And the net result was a box of blueberries kind of flipped out, and it flipped open, and blueberries were everywhere on the floor, and the dogs came running in, and they wanted to get them, and I needed some help. I said, I need help. I need to get these things. Has anybody ever done that? You could let your dogs eat all the blueberries, but then I worry about if they're going to get sick on them or something. So we rushed in and picked them up. And I know if my hand would be normal, I wouldn't have had that issue, but I took a chance and I lost. Okay, so in this example, we have a sinusoid at capital omega naught. We're going to play fairly. We're going to make sure the frequency of the sinusoid is less than the sampling rate over 2. So we'll draw the pictures out, and we'll show with our sinusoid all of our spectral translates. The solid one is at omega naught. That's where it sits naturally, and then the dashed one is at the negative frequency. And then we'll just simply pick up the translates and lay them down centered at minus omega s and plus omega s, and say, good enough. We visualize a recovery filter that's ideally going to cut off at the folding frequency omega s over 2 is sitting in here. This and this are inside that box. They're not confused. They're where they're supposed to be, so there's no aliasing. So we go up here and just say, okay, suppose omega naught is greater than pi over t or omega s over 2, they're equivalent. What happens is, leave this in red, that's where our sinusoid at the input is sitting now after we sample at a lower rate, and our ideal recovery filter is going to pull out the aliased frequencies and give us to those at the output of our processing, and we're going to be at a loss because we have committed the crime that I always think about in sampling theory. We've aliased, right? And I guess if you think of the word alias, in Python we're always aliasing the name of an import into something that we can remember easier. If you watch a spy movie from a long time ago, probably not something that anybody thinks about anymore, is people have aliases, right? They go by more than one name. And I guess on the internet, maybe with phishing and everything else, there's aliases. I don't know. Is that commonplace? I'm trying to think. Where else does alias get used in our life? Okay, that's right. I don't play them, but my son does. My son has his PlayStation 5 or whatever it is. He plays some very sophisticated video games, and I guess there probably are some aliases in there. I'll have to ask him about that. I didn't grow up in that era, but my sons, and I have twin sons, so they grew up and playing video games, and even though one lives in Denver and now has a girlfriend and doesn't come down here as much anymore, my sons, who did they play video games against? Each other. I mean, that was just the standard classical thing that people that like video games would do. They would play against each other, or they take turns playing against whoever the virtual player is on the game they're playing. At any rate, we've got aliasing. So we'll get more into that later, but let's just state the theorem, which you've seen before. It says that omega s must be greater than twice the highest frequency, and that's what I've been saying. That has to be greater than 2 times the highest frequency. Omega n, though, which I also call the folding frequency, is like the folding frequency. Omega n has to be less than the folding frequency. So I would always think if that's the highest frequency, we just have to be less than the folding frequency. So you can state it either way. You can move the two to one side or the other. What I want to do is this before we leave, but I want to show you a demo of something that I think is kind of fun. Question?
Yeah, about the project. When do you expect to have the project ready for us to start? And also, I was looking at the project list, and there's like multiple projects in the
Multiple problems, for sure.
Isn't there multiple, like, project 1, project 2, like, and then 5?
There's only project 2, and project 2 will be due finals week, and it's going to be this, whatchamacallit, filter bank processor for radio. AM radio is what I've decided I'm going to go with. It's very canned up. I give you a big file, which I have to distribute on Slack. It's a very large capture from a radio receiver, and that will be it has a set of problems with it. It was worked by one student. Last year it was a prototype project, and one student, she chose that one, and everybody else chose something more traditional, but I think, and I know it worked well. She did well on the project, so she liked it a lot, and I'm going to make you all do the same project this year. It'll be easier for me to grade it. But it's a fun project. So I could go look at the project right now, and I could tell you which is going to survive. I can do that. If that's of interest to you, I can go down here and look at. And by the way, these projects are very full of info. There's a large comment section that has a lot of hints and things at the end of it, and then this will change up, but this just tells you how the points are distributed to know that this one has 290 points in it, but I did eliminate a problem. I eliminated this polyphase decimator last year, so that one came out of here, so the number of points was less. But in terms of what I know I'm wanting to go with right from the get-go, my computer is struggling loading the content in right now. I'm moving the page, and it's not able to put it all in there. Definitely going to do that problem. This one I've been hinting at you to get started on writing code. The sooner the better. Definitely going to do this problem because this is going to put you into a mode of understanding more about multi-rate processing, and which is what we're getting into right now. The down arrow with the 4 means we're going to decimate by 4, keep every 4th sample, and then the up arrow means we're going to insert extra samples to increase the sampling rate. So this is very cool. I like this problem a lot. It makes you have to think a lot and think in the frequency domain. So that one you'll work. This project is not going to come back, but I have something in place. But I'm not absolutely positive it's going to be a fixed point filter based on something I ran into in the last few months on my project at my job that is something I should have understood a long time ago, but I wasn't forced into it, so I'm going to let you get forced into something that it's very simple, but I think I can make a cool problem out of it, actually. Fixed point arithmetic, something that most of us probably don't do much of. This problem may also go away. It's been around here for a long time, but it's a notch filter, but the notch filter shows up in another problem, so I'm not sure this one will survive. What I'm thinking of doing is having one less problem like last year, but I'm going to maybe replace this by this fixed point filter I was talking about. And this is the multi-part problem using Pi Audio Helper. So you'll work all of the parts of this one.
And we're definitely doing that one.
Definitely, yeah. This is way too much fun. I'm telling you the honest truth. It's a lot of fun. I mean, it really, you get to listen to things and you get to tune things and you get to, and I'll demo part of this. Not next week, but probably the week after I'll demo part of it, because I have a sample in here that's actually built out in the sample notebook that actually runs, and you get to play with it. You get to filter, add noise, and then make adjustments and listen to it, and that's part of what you do right after you write the code. You get to listen to what you're doing, so it's pretty nice. So that's where that's at right now. Okay, I'm going to now jump over to this, and I've got this folder called Zojo Apps. So we'll look at pole zero geometry and PZ2 later when we're in chapter 5. But right now, these two are pretty interesting. And these were also my first goes at writing GUI applications using a development tool. So these first two are very simple, but the other two are more complicated. They involve mousing things and moving things and dragging stuff around, things I'd never tried before. I never tried writing a GUI app from scratch that had interactivity in it. And no, it's not a video game or anything like that, but still it's an engineering application. This one, though, I like quite a bit because we were just talking about sampling theory, and I can remember a long time ago when I taught a short course here with another 2 faculty members for industry, learning about basics of DSP, and I remember somebody in the audience was arguing that sampling theory is something along the lines, sampling theory is a lie. It doesn't work. You can't do it. And I wasn't the one that got asked this question, but another faculty member that I worked with was, and it was like, okay, this guy was pretty adamant, and it was a challenging thing. I mean, that happens though, right? You've been in a class where somebody is arguing a point, and I won't try to go into the details, but the person is really being put on the spot and has to work hard. So here I've got I can change the frequency with this slider, and I can change the phase with this slider. So here, I'm sampling at a 1 hertz sampling rate. So I'm changing the frequency of the sinusoid over here. And as I increase the frequency of the sinusoid, I have less samples per cycle, and I'm going to reach a point, like right there, for example. I've got 4 samples per cycle, 1, 2, 3, 4, and then I start over again. So where am I at here? If I keep going up in frequency, I'm going to eventually reach the Nyquist, right? Like right there, I've got 2 samples per cycle. We have to be just slightly less than this. If we're right on that mark, we're going to have a really hard time reconstructing, and I'll just demonstrate that. If we're right at that point of exactly 2 samples per cycle, and the phase of our sinusoid slips over, what's going to happen? We get nothing, right? So that was what this person's argument was, part of this, as I'm recalling, but that's okay. That's right at the folding frequency. That's okay. I mean, we can get away with that's only one frequency. So, but we have to be slightly less. If we're slightly less, then what we're seeing here as we go out over time, the samples are the sinusoid's asynchronous relative to the sampling rate. So this value is eventually the sample values are eventually going to build up really big, and then it will slide through and it will go back down again. But we'll be able to reconstruct a sinusoid out of that. It will work. We also see, though, I'll take this back to the 0 point. We'll also see as we slide up here, now we're over the folding frequency, and now our brain is just seeing a bunch of random samples. But at some point, as I move this up higher and higher, your brain is going to shift, and you're going to see the alias, the lower frequency sinusoid. Now I'm just going to keep going, and you're going to maybe see it at some point. I'm not seeing it right now, though. I've got to get a little bit higher in frequency. Now I'm seeing it. I'm definitely seeing it right now. Do you see a lower frequency sinusoid running in the background of these samples? If I take this up even higher, though, then it's going to become it's more and more obvious as I go up higher and higher. I'm getting close to sampling frequency itself with my input sinusoid. So I go all the way up here, then I'm just going to have DC again, but you're seeing the alias, right? Everybody see that? Now if I click this button here, then I'm going to draw correctly through that, so it's the alias component. So now if I draw through there, I'm seeing the alias frequency. It's a lower frequency. When I drop all the way down here, right there, now I've got 2 samples per cycle, and now here it was going down in frequency due to the aliasing, and if I go below this point, now it's going to go down in frequency again. But that's we're now not aliasing. So, do you want me to do anything else? I mean, it just gives you a visualization of something. And I know there's other things people have done, but this to me, I kind of like that there's different things you can do with it. Turns out writing this in software is actually pretty easy, but I had to learn something, and I actually wrote a graphics package to do the plotting, object-oriented plotting, which was a new experience for me. I made it kind of like MATLAB, because at that day I was doing MATLAB stuff. Turn that one off. This is now a frequency domain, so now we've got this slider controls the sampling rate normalized by the bandwidth of the signal, and the bandwidth is plotted as 1 here. So as I do this, I'm increasing my sampling rate, and these are all the spectral images. I'm not applying an infinite number, but we're just seeing as we increase the sampling rate, eventually we get up to the folding frequency. Go higher. Now we're sampling at greater than twice the highest frequency. We don't see any aliasing, right? And if we oversample, then we have more of a guard band in there. But if we go lower, then we have the overlap, so we have the aliasing. Everybody good with that? This just reinforces what we've already talked about. Now I'm going to turn on a bandpass signal. And so if we go back down here, we'll see we're starting with a signal that is like a radio signal that starts at some frequency and then stops. And this one is just a narrower version of the same thing. I'll stay on that one. And this is the way a lot of software-defined radio works. If you assume you have an analog input filter, a SAW, surface acoustic wave filter, or something that's got a nice defined pass band and blocks outside that band, and then we can invoke the bandpass sampling theorem, which it's in the book in homework problems, but I'll talk about it a little bit more in the notes or in the Jupyter notebook. We can sample at less than twice the highest frequency. In other words, we don't have to sample at 2, which is where we were at before. If we slide all the way up here, all the way up to 2, or I guess 2 is right in here, this is sampling at greater than twice the highest frequency, but that's kind of overkill. What we see in this case, we can sample at less than twice the highest frequency, like right there, because if we lower it down enough, we're not interacting. We could filter out the blue spectrum if we wanted to, or maybe in software-defined radio, we're after the red one. And let's just see how that works. If I lower the sampling rate down even more and more, I can keep going lower. I'm still good. Still good right in there. And now I might decide I'm going to recover these two right here if it's a radio signal. Now they're maybe they're inverted somehow or another, but a bandpass filter would recover the original signal, or this from a radio signal standpoint, just recovering that might be useful too. So undersampling does work for signals that are band limited, and this is a visual of that. You maybe have never thought about this before, but this is how software-defined radio really works. It uses undersampling and bandpass filtering. And if the signal had a wider bandwidth, then we have less bands that we use. We have to sample at a higher rate to fit it in, but this one fits in just at a higher rate in order to fit the wider signal in. Of course, there's bands that are no good that overlap each other, but there's a formula for this, and this is in the notes, or it's in the Jupyter notebook for chapter 4. Okay. We'll probably look at more of these things sometime in the future. Like I said, in chapter 5, we'll look at the other 2 applications in there. They'd be on the website, but right now I can't put up very big files. So the DLL library files for the Zojo development environment are too big for the WordPress website the university has given me to use. The largest file size is 8 meg, which is not very big, but I can send it to you if you're interested. I can send you this stuff. Okay, so one of the last things we'll be looking at here is relating, going back to the very beginning, we did something kind of artificial, or we did something out of convenience, but we really didn't go anywhere with it. We said we can bring in an analog signal and we could get it into this discrete time domain. What we didn't do is connect the spectrum out here in the analog side to the DTFT of our sequence X of n. So we need to do that step. We don't really want to be looking at, like this business over here, we don't really want to be looking at this. We want to be looking at what is in the DSP domain, or the discrete time domain. So we're going to basically connect some more dots. And that's what this topic is. So this topic says relating x of e to the j omega, and I should write that in here, that corresponds to that. And then, of course, that is already our x of c of t. So what we're stuck at right now is we have this, but we have to do a step in order to say it's the same as x of e to the j omega. So there's another transform pair in the table that says a delayed delta in the time domain is a e to the minus j omega t naught. So we can use that as a means of getting the spectrum of the sampled signal directly. So we'll use this theorem repeatedly to say that x sub c of nt, which is in place of a in the frequency domain now, will be times e to the minus j omega t naught. So we have that. And then we notice that x of n is the same as x sub c of nt, so that's right up in here. So that's there, and then down here we'll make that change. We'll put x of n in there. And now all we have to do is do one variable transformation. We'll say that what we had before, x sub s of j omega, was really just is the same as x of e to the j omega if we replace little omega by capital Omega times t. So we make that substitution, and then we get, after the other expansion in between, we finally get down into here. So we have a means of saying what is the spectrum of the signal, discrete signal x of n, and how does it relate to the analog spectrum coming in. And it's just a frequency translated version of it. But now we're in the true discrete time domain. We're not stuck just looking at this ideal sampled waveform in the continuous time domain. We're actually looking at something in the discrete time domain. And this allows us to do all the other problems that we have in the chapter, of course. And I'm going to just do something that's kind of classical at this point. So this is the fundamental relationship right here, which says we could go rearrange it like that, and we do that frequently in the plots and so on. So we have different things we can do with this relationship. So we get a scaled version of our original analog spectrum, x sub c of j omega, I guess that should be. But in reality, I guess this is maybe confusing. This should be, that'll go away. We can do that, and we can make the, the variable substitution that little omega is capital Omega times t, and then we can draw other axes down here. So we could have little omega, this will be and then the additional axes down below F in hertz, we can have 0. This will be Fs. So we can get all of that involved because now we're going to replace capital T by 1 over Fs. So we can have our different means of looking at things in the different domains. In the continuous time domain, we have the top axis, capital omega. The axis I prefer is this one, frequency in hertz. And then we can move into our digital frequency axis, little omega. So when you start drawing pictures and start working through problems, you're generally working with different axes. It's the same plot up above. And of course, this case, it's x of e to the j omega. But the spectrum component that's centered at 0 is 1 over t times x of j capital omega. So I started drawing that originally. So there's one more topic in here that I'd kind of like to go through, but I don't know. Are there any questions right now? I know part of what I'm doing tonight is polluting your brain with thoughts that get in the way of taking the exam, but we have to be multiplexing. So we're multiplexing. This stuff will load in there, and that's going to shove over to your temporary memory and hopefully not be gone until after the exam. But these frequency axis stack-ups are very useful, though, to me. And of course, when we come back out to the D to A converter, we're talking about what lies in this band right here, and 0 to Fs over 2 is what we think of for a real signal. And if it's a complex signal, like a radio waveform, it'll be something sitting between plus and minus Fs over 2. And that's kind of the domain most of the stuff I've been working in involves, is the so-called complex baseband, which you'll get a chance to see that in the second project a whole lot more.
What did you write under, like, in red over the 0 axis for the omega?
Oh, here?
Yes.
That's just a 0. I didn't write it very well. It's DC, so I can delete part of it. It's just a perspective. The bottom two are the ones that I personally prefer, but sometimes you have to keep it straight, obviously. I mean, there's actually one more on there too. If we actually wanted to be technically more perfect, we could get rid of that. We could have big F for hertz, and then we could have one more axis down below here, which would be little f. So this would be 1, 1/2, 0. That very last axis is more like the plotting I was doing in Python, where I wanted to plot just between 0 and 1/2. That's omega divided by 2 pi is what that one would be. But I'm kind of partial. I like lowercase f for frequency in hertz. But if I wanted to be consistent, big capital F there and capital omega kind of go together in the analog domain, and little omega and little f go together in the discrete time domain. So a little topic that's not really very long, it's just sort of extending off of what we've been talking about. It's possible to reconstruct a band-limited signal from its sample. So we know that the analog signal started off in this form. The sample started off in this form. So then we apply a reconstruction filter to this sampling waveform, and we think about convolving with our that low-pass filter that we were talking about before the break. And that convolution becomes a sum involving the time-reversed impulse response. And then we think about what was that ideal reconstruction filter. It was a sinc function, because we're talking about something that's rectangular in shape. It's just plucking out the spectrum that runs from minus fs over 2 to plus fs over 2, or minus omega c over 2, and so on. So that becomes a sinc function, and if we plug that into our equation now for representing the reconstruction in the time domain, we're getting back an analog signal by taking the sample values in the discrete time domain, and we're going to convolve that, or basically weight that with the sinc function. So the sinc function is the ideal interpolator to put things back together. And I have a little picture that's ways off here yet. This picture right here kind of shows you what that kind of looks like. You start off in the analog domain, you end up with the samples of it, and then if you take it back out to the deltas in the continuous time domain, at each delta you're placing that sinc function reconstruction filter, and all of those if you tie all that together in the continuous time domain, you basically are reconstructing your original waveform using all those sinc function shapes. It's like in the analog domain, they hit that filter and they produce the wiggly waveform, and it gets hit again at the next sample, and then they're all combining together. Does that kind of make sense? Why did I get excited about this at one point in my life? It's because I was teaching a class out at then Hewlett-Packard, now Keysight, on digital scopes. And they make digital scopes here in Colorado Springs. And one of the things that was going on in digital scopes in that era was, it was called random repetitive sampling. And what they were doing with that is they were getting just a few points that would come back from the oscilloscope, and then in order to make the screen look more like an analog oscilloscope, they were reconstructing. They were using something like this, only it was a finite duration pulse, so that they could actually draw the picture on the screen, so that an engineer did not feel uncomfortable looking at dots. They wanted to look at a smooth waveform. And they used a proprietary reconstruction filter that had a finite number of samples in it, rather than this is based on a sinc function that's totally non-causal at that, because of the sinc function having the tails at minus and plus infinity. So they had something that was proprietary that they used in their oscilloscope to reconstruct it. Now, I don't know what they use exactly now, but the idea still holds today. When you're using an oscilloscope, you don't just see dots on the screen. You see it's oversampled a lot, so it fills in to look like an actual continuous time waveform. But it's still discretized, and the reconstruction filter idea, which is talked about here, kind of helps explain how that can be made. And that also defines the second box that we haven't talked about yet, and that's right here. We take the sample values x of n, we convert them to an impulse train, then we can send it through an ideal reconstruction filter, and then that is the opposite box. That's the D to C converter box that has a sample spacing t in it. So one thing weird about this box, I'm just going to point out, and I'll have to talk about it again. A capital T was put inside of this reconstruction filter to make up for the 1 over T that was at the very beginning when it gets sampled. So this picture right here is sitting up inside this box. So some of the pictures you end up drawing for some of the homework problems, you just have to remember that to finish, if they ask you to draw out in the continuous time domain, they might ask you to draw this spectrum. you have to remember to apply that T when you transform from the line before to the bottom line. So you might go from x of n, and then you go to x of r of j omega. You'll put in a capital T in there to gain scale it back, and that just takes that out that was in there before. So now we're back to where I said we would be at the end. Amazing. I said I'd get this far, and I don't want to push any harder myself. It's a good place to stop, but I'll take questions if there's anything. One of the things I posted after the little session I had last week is that one line is now missing, right? Put that in Slack. Miles typed that in faithfully, and it totally blew things up for him, right?
We found that out.
Yeah, we found out right away, and I have it commented out too. I don't know why it was in there, but things change over the lifetime of this software, so I might have had to use it at one time, and sorry about that. And then I gave you that file if you don't want to see those pink bars when you're doing a pole zero plot. That's in there, that warning. I don't know why it's not showing up here right now. Somewhere it's down here. I don't even know where it went to, but the file was attached. Did anybody start doing that? I attached a file. I don't know. I'm not seeing it right now. It's sigsys.py. I just made a fix to it, and yeah, it's right here. That's the file. You can just drag it out of there, download it, and then you can follow that instruction that I gave. You just have to link to it directly, because I don't think we'll patch it in the Scikit project, which means it's a lot of steps for my co-developer to do to change one little line and then push it back up to the various sources and make them do it. It gives you an idea of how software gets upgraded, not at lightning speed. It kind of takes some time. He was very good about doing it, but then he got married and he's doing what...
It went downhill.
Yeah, exactly. So have a good evening. I'm going to sign off.